This is example 12-5, bump in a channel. So we have flow going from right to left. And it's a rectangular channel with a width of 1.5 meters. And then there's this bump in here. And so at this bump, the water level is going to decrease to y prime. And then we're asked if the flow upstream is, to make sure that it's supercritical, we need to know what the height at y prime is to transform to supercritical flow, and then also what the location, what the depth at location 2 is. Now to check if we are supercritical or subcritical, we can start out by finding what the critical depth is. So we can say YC is equal to Q squared over B squared times G over 1/3, or raised to the 1/3 power, I'm sorry. All right, so we get 4.5 cubic meters per second squared divided by the width is 1.5 meters squared times 9.81 meter per second squared raised to the 1/3 power, and that gives me 0.97163 meters. All right, so we can say that YC is less than, if we call this one maybe location 1 and this location 2, less than Y1, which of course means that it is, YC is less than Y1, so that means it's subcritical. Usually I write it the other way around, that's why I stumbled, right? Usually I would write Y1 is greater than YC, and then that way it's subcritical. But regardless, right? So if it's larger than the critical depth, it's subcritical. If it's less, it's supercritical. All right, so that was the first question, right? So we did show that it is subcritical. Now we're asked to find the depth at the bump, right? So how high the water is above the bump. Well, we know for a transition to happen from subcritical to critical to supercritical, or the other way around, that YC has to be equal to, like Y prime has to be equal to YC. All right, so we can just write that down. Y prime is equal to YC equal to 0.97163 meters, or 0.972 meters. That's our depth there. And then the last one is what is the depth downstream. That's the shortest part of the question, but of course it's going to take us the longest, right? Because again, just like with other examples, we'll calculate what the specific energy is at 1, we'll calculate what the specific energy is at 2, and they have to be the same because there's no change in elevation. All right, so we can start out at 1. We can say E1 would be V1 squared over 2G plus Y1. Now we're not given what the velocity is, so we need to use the flow rate. So we'd have Q over A1 squared over 2G, and then up here plus Y1. Be careful. All right, that would be Q squared over 2G times A1 squared plus Y1. And that's then Q squared divided by 2G. A is a rectangle with the width and the depth at 1, so that would be B squared times Y1 squared plus Y1. Good thing here is all of those are values that we know, so we can just plug those in. And we can say that is equal to Q was 4.5 cubic meters per second squared. 2 times 9.81 meter per second squared. The width is 1.5 meters. 1.5 meters. And the depth was 2 meters. Right, squared again because we had a squared. Plus 2 meters for y1. And that gives me 2.114679 meters. All right, so that's our specific energy at 1. We can do the same thing for 2. So we can basically make our life a little bit easier. We don't have to reevaluate this whole thing. All right, we can say E2 would be, I'll just write the first one in here, so it'll be V2 squared over 2G plus Y2. And then we can do exactly the same steps, right? So it'll be Q over A2 squared, and so on, so on. So we'll just take the last step here. So that would be Q squared over 2 times G times B squared times Y2 squared plus Y2. Now the big difference, of course, now is that we don't know what Y2 is. That's what we're trying to find out. But we can say all this, E2 will have to be equal to E1. And with that, we have an equation that only has one unknown, y2, so we can start solving this for y2. All right, so we can multiply everything by y2 squared. E1 times y2 squared is then q squared over 2g b squared plus y2 to the third power. Because y2 times y2 squared. If we solve that, I'll put it all on the same side. Right, then we'd have y2 to the third power minus e1 y2 squared plus q squared over 2 times g times b squared. Oh, let's not forget, equal to 0. All right, with that, again, the only unknown is y2. So as soon as we fill out all the numbers here, we can go ahead and solve it. So that means we have y2 to the third power minus the e1 that we calculated up there. All right, so that was 2.114679 meters times y2 squared plus 4.5 cubic meters per second squared divided by 2 times 9.81 meter second squared times the width was 1.5 meters squared. Equal to 0. Which means we get y2 third power minus 2.114679 meters times y2 squared plus 0.458716 meters cubed. Real quick to the units, right? Of course, each of these terms have to be meters cubed in the end, right? Because we have y to the third power. Depth is length, so that's where we get that. All right, so with that, we can go ahead and solve. Again, use whichever solution technique you want to have. We can say y21 is equal to 0.53967296 meters. y2 is equal to 2 meters. And then y23 is minus 0.424999406 meters. Of course, the last one drops out. It's negative. Can't do anything with it. And now we have two solutions, right, that are both physically possible, right? The 2 meter one or the 0.54 meter one. And so the picture that we're shown here would be the case where we do get the transition, right? Where we go from subcritical flow to supercritical flow along this block, right? So we'll say for this one, we'd say Y2 is equal to then 0.540 meters, right? That would give us a flow. Let's see if I can sketch this halfway decently, right? Where we kind of do this. This is the bottom right. Now the other case, like the 2 meter one, right? That would be something where I have my bottom here, have my bump, have my water coming in, it dips down and dips back up, right? I bet you've seen that in a river or something, right? If there's a submerged rock or something, you can kind of see that the water level dips. All right, but here, I think we're looking at this case where we're transitioned from subcritical flow to supercritical flow. All right, that was example 12.5, where we figured out how deep the water was above this bump, and then also how deep the water was once it's transitioned from subcritical to supercritical flow.